Look around you right now. Seriously, take a deep breath. Every single day as we breathe, touch, and eat, we're interacting with this massive, hidden, microscopic world. The air is literally filled with floating pollen lit by sunbeams, tiny particles of house dust, pet dander, and microscopic mold spores. Now, for most people, interacting with these thousands of proteins is completely harmless. You wouldn't even know they were there. Yet for some individuals, these exact same invisible substances trigger this massive cascade of reactions. We're talking sneezing, wheezing, eczema, or even life-threatening emergencies. So the big question is, why? I absolutely love this perspective from Dr. Bahubali Ingale. It perfectly sets the stage. He says, science teaches us a profound truth. The most powerful things in the universe are often invisible. Gravity cannot be seen, yet it holds galaxies together. Electromagnetic waves are invisible, yet they connect our world. Oxygen is unseen, yet every breath sustains life. In much the same way, the air around us carries countless microscopic proteins. Most pass unnoticed, but in certain individuals, these tiny particles awaken an extraordinary immune response. Today, let us journey into the invisible world of allergens, the hidden triggers behind allergic diseases. Okay, let's dive right into this microscopic journey.
Section 1. The invisible world. Defining our microscopic characters. To really get a grip on this topic, we first need to define the cast of characters operating in this hidden space and ask ourselves why seemingly harmless things cause such severe biological alarm bells to ring.
Let's start with some basic yet absolutely critical terminology. In immunology, we throw the word antigen around a lot. An antigen is really just any substance, like a virus or a bacteria, that triggers your immune system to respond. It's a very broad umbrella term. But an allergen, well, that's a very specific type of antigen. It is a generally harmless substance that triggers an abnormal allergic response in susceptible people. So while every allergen is technically an antigen, not every antigen acts as an allergen.
But what gives these specific proteins their superpowers? How do they alert the immune system in such an extreme way? Well, these microscopic characters share some very specific traits. For one, they're highly soluble, meaning they dissolve incredibly easily into the wet environments of our eyes or our lungs. Many also have amazing environmental stability. They just don't break down easily. Some even possess protease activity, essentially acting as tiny enzymes that can slice right through our cellular barriers. Add in high heat and digestion stability, and you've got a resilient microscopic protein that can literally survive the acid bath of human digestion long enough to trigger an immune alarm.
Moving on to Section 2. Meet the allergens, the grand catalog of invisible triggers. The sheer diversity of what we're dealing with here is staggering. We're going to open up a grand catalog of these triggers, breaking them down category by category. Let's start right inside our own homes with our invisible roommates. You've got the famous house dust mite, which sheds major proteins known scientifically as DIR-P1. Then you have common pets dropping specific proteins like FeL-D1 from cats everywhere they go. Add in indoor molds and, even cockroach proteins, and you quickly realize our most private, enclosed spaces are just bustling with invisible activity. Just to give you a sense of scale here, a single microscopic dust mite produces about 20 droppings a day, and every single one is packed with these highly stable, allergy-inducing proteins. It's wild.
But step outside and the landscape completely changes. Out here, our invisible characters are dictated by seasonality and regional geography. Spring brings tree pollens like birch and oak. Summer brings grass pollens like timothy and Bermuda, while late summer and fall are totally dominated by weed pollens like ragweed. There are also outdoor molds thriving in damp soil, right alongside agricultural dusts. These are airborne proteins expertly designed by nature to travel for miles on a single breeze.
Then we have the allergens that cross our barriers because we either ingest them or they're quite literally injected into us. Food allergens cover a massive spectrum: milk, eggs, peanuts, tree nuts, seafood, even specific fruits and vegetables. And then there are the insect allergens. This isn't just about breathing in insect dust. We're talking venomous insects like wasps and fire ants. They completely bypass our surface defenses and inject their protein triggers directly into our tissues, causing immediate and sometimes incredibly severe reactions.
To wrap up our grand catalog, we have to look at our jobs, occupational allergens. Certain professions come with their own unique hidden triggers. Healthcare workers, for example, might develop allergies to latex or clinical chemicals. Laboratory workers are frequently exposed to specific animal proteins. Bakers are breathing in flour and enzymes daily, while carpenters might react to wood dust. It beautifully illustrates how our environment, and specifically our daily habits, dictate our exposure.
All right, Section 3. The allergen families. Discovering hidden relatives. Now, this is where the story takes a really fascinating turn. These invisible characters aren't just isolated, independent entities. No, many of them actually belong to closely related biological families with shared molecular structures.
So, the crucial point here is understanding the difference between co-sensitization and cross-reactivity. Co-sensitization is just having two completely separate allergies at the exact same time. Say you're allergic to dust mites and peanuts. The two have absolutely nothing to do with each other, it's just bad luck. Cross-reactivity, on the other hand, is when your immune system's antibodies recognize shared structural parts, which we call epitopes, on entirely different allergens. It's essentially the immune system getting confused by two proteins that look exactly like identical twins.
And this identical twin concept explains so many medical mysteries. Take the PR10 protein family. You might have a patient with a severe respiratory allergy to birch tree pollen, but suddenly, when they eat a perfectly harmless apple, their mouth starts to itch and tingle. Why? Because the apple contains a PR10 protein that looks almost identical to the birch pollen protein. This is known as oral allergy syndrome. Or look at tropomyosins. A person allergic to house dust mites might suddenly react to eating shrimp. It's biological mistaken identity. By understanding these protein families, we can actually predict these seemingly bizarre allergic connections.
Section 4. The Immune Misunderstanding. Inside the human body. We've spent a lot of time out in the environment cataloging these particles. Now, let's transition into the microscopic world inside the body. This is the story of a well-intentioned but ultimately overprotective guardian, your immune system.
First off, we have to address why most people can just inhale a cloud of pollen and go about their day, while others are totally miserable. Susceptible individuals possess a very specific combination of factors. It starts with genetics and a trait called atopy, which is just a genetic tendency to produce allergic antibodies. Add to that epithelial barrier dysfunction. That means the protective barriers of their skin, gut, or airways are slightly leaky, which allows these proteins to slip right in. Combine that with alterations in the body's microbiome and the loss of natural immune tolerance, and well, the stage is perfectly set for an overreaction.
So how does a full-blown allergic attack actually unfold? Let's trace it step by step. It starts when an allergen breaches that leaky epithelial barrier. Instantly, specialized immune cells grab the intruder, misinterpret it as some dangerous parasite, and sound a massive chemical alarm known as a Th2 response, releasing signals like IL-4, 5, and 13. This activates B cells to start churning out specific IgE antibodies. Think of these as biological weapons. These weapons then attach themselves to mast cells, arming them like hidden landmines in your tissue. Upon re-exposure, the allergen steps right on those landmines, causing the mast cell to just explode with histamine, triggering that immediate, miserable allergic reaction.
Section 5. Playing allergy detective. Identifying the invisible culprits. So if we know exactly how the body reacts, how do we figure out what it's reacting to? With thousands of potential triggers out there, modern medicine has to act as a highly sophisticated detective to identify the exact invisible culprit.
To find the culprit, it always starts with the clinical history. We have to correlate exactly when and where the patient feels sick. From there, we use skin prick tests or specific blood tests to hunt down those armed IgE antibodies. But today, science goes even deeper, with component-resolved diagnostics. We don't just find out you're allergic to peanuts, we can pinpoint the exact protein molecule inside the peanut you are reacting to. We can tell whether it's a major protein causing severe risk or a minor protein causing mild symptoms. But remember, finding an antibody on a test must always perfectly align with the patient's actual real-world history for it to mean anything.
Ultimately, demystifying this invisible microscopic world of proteins is our foundational first step. By knowing our enemy, its molecular weight, its family tree, and exactly how it tricks the body, we can finally begin to fight back. And that leads us nicely forward. How we actually treat these reactions, control our environments, and avoid these invisible triggers will be the complete focus of our next explainer.
But before we wrap this explainer up, I want to leave you with something to really chew on. Think about the incredible complexity we just explored. If our immune systems evolved as these brilliant, highly sophisticated protectors against deadly diseases and parasites, what underlying evolutionary purpose could there possibly be for them to fight so fiercely against a harmless, invisible speck of dust?